Hey guys, how you doing? Let's see your faces. Come on, people. Let's be a class. Thank you, Audra. Elijah. I missed you, Elijah. I haven't seen you since Wednesday. Christopher James, still not smiling. That's okay. You don't have to. Vanessa, chilling on a bed. Good for you. Farouk, I don't get it, Farouk. You're a good looking guy. Let's see your face. Come on. There he is. Isn't he a handsome man? Ladies, let him know. Oh, I'm just being a jerk. I try to be a matchmaker. See, that's part of my job here at Plattsburgh State. I don't know if you read my job description, but it was there. Okay, so I would like to start class today with the quiz that I promised you on Wednesday. So it's 3 essay questions. I emailed it to you and I put it up in Moodle. So either go to Moodle or go to your email and pull it up. I'm going to give you until 20 after to do that, and then we'll talk about it, okay? And then we'll start mouse development. I know you've been excited about mouse development, so we'll do that next. So go ahead and do that. If you can't find it, I'm going to mute right now and turn my camera off. But if you can't find it, I can still hear you. So hey, Dr. Slish, where the hell is it? Give me one of those. If you just showed up and you don't know, there is a quiz in Moodle that I need you to do, and then we're all going to talk about it in 6 minutes. 6 minutes. Okay, let's talk about this. Shall we do this for bonus points? Seems like nobody does anything except for bonus points. Bring your faces up again so we can talk. Okay. So first question. Let's not do it for bonus points. It's too complicated to figure out at the last second. Okay. First question, Farouk. Imagine you could control the process of chick development from conception as you can with Xenopus. What would you do? What do you think would happen if you didn't allow the egg to rotate in a shell as the shell was applied?
I'm not really sure, but the rotation of the egg that dictates where the Kohler sickle is going to be. So will it affect the anterior posterior axis? Or is it about like the primitive streak, the formation of the primitive streak?
I would guess any of that. I don't know the answer, by the way. I just made this up. So your guess is as good as mine, but you're right on track there. The whole idea of the rotation is it makes the Kohler sickle go to a specific place, and that's where the primitive streak starts, and that causes the AP axis. Okay, now if that's not rotating, is it still going to develop a Kohler streak? I don't know. Where's it going to develop? I don't know. Because in the book, even it says they don't really know what causes it to go there. They just know it shows up there during their rotation, and because the thing is tipped up this way. So if you didn't allow it to tip up, it might not form a Kohler crescent or whatever. That may form all the way around, and it'll totally mess the whole thing up. Who knows? But the important point, what I was hoping to get from you, and I did, was that the rotation determines where that Kohler sickle ends up. Good. Bad news, Yusuf. I can see your face right now. What are the three different signal transduction pathways that are required for primitive streak initiation and progression?
The three different pathways?
Yeah, give me as many as you can think of there that are involved in that process.
Didn't we talk about one of the pathways for Xenopus or no?
No, here, I'm just talking about chick here. Although
I really don't remember.
Same pathways are used in Xenopus, but there's no primitive streak in Xenopus. All right, let me bust someone else.
Is it going to be
Who's this? Who's
like
talking?
I noticed.
Who is it? I don't know who it is.
Oh, it was Evans.
Evans, okay. Evans, Cujo, what do you think?
Is it going to be the reception pathway, the transduction pathway itself, and then the response?
No, I mean specific pathways, hormone, receptor, turning on, signal transduction.
Okay, so.
Is it like TGF-beta like pathways?
That's one.
Is one Wnt and VG1?
Wnt. VG1 is another TGF-beta like one. So we got the Wnt pathway, TGF-beta like pathway, and
is it FGF?
FGF. Right. So those are three separate and very different signal transduction pathways. Your TGF-beta turns on the SMADs, the Wnt turns on beta-catenin, and the FGF turns on MAP kinase, which turns on other transcription factors. So we've got three different signal transduction pathways involved in that process. Okay, I want to bother Michelle Simmons now because I think she's getting a little cocky. She knows everything. So Michelle Simmons. Retin-A, a derivative of retinoic acid, is a prescription drug used for severe acne, sorry about that. It is a topical lotion whose mechanism of action is inducing the rapid turnover of cells, preventing new pimples from forming. So basically it makes cells divide really fast and then pimples don't have a chance to form and it clears up your skin. This drug is strongly contraindicated for women who are pregnant or at risk of pregnancy. And that's a risk, let me tell you. Why do you think this is, Michelle Simmons?
So I said that since that it causes a rapid turnover of cells, that maybe when, like for the developing embryo, the cells, that would cause the cells to have a rapid turnover, so the embryo wouldn't be able to develop correctly. There'd be developmental.
That's a good answer. I mean, it's not what I was looking for. I would have to give you full credit for it because I think I didn't make the question specific enough for what I wanted. But what did we talk about that in class last time that would be related to this question? How about Elijah?
Is it that retinoic acid inhibits FGF?
Yep, it inhibits FGF, and that would mess things up. And also, what processes is it involved in there where it's inhibiting FGF?
Is it neurulation?
Yeah, during the somite formation of neurulation. So you can see how important that retin A is in that process because it helps to form the gradient during the wave front of the node regressing as neurulation happens. So if you had an overload of retin A, it would block the FGF and the Wnt. It would probably stop neurulation altogether, right? Because it would block that thing from moving. But like you say, Elijah, you know, FGF is so important for so many developmental processes, and retin A inhibits the production of FGF. So A or B, it's definitely going to screw up that embryo. Okay, good, good. I don't know about you guys, but I got them all right. So I'm getting bonus points again today. Oops.
I did so bad.
You know what? You gotta study this weekend. You'll be on top of it. You know, I've got some quizzes. I don't even know what they are in Moodle that I have hidden. Maybe I'll just open some of them up this weekend for you to play with, and then we can talk about them on Monday. Okay, but we've got 20 minutes left in class. There's something I want to talk to you about. I'm not sure if I'm gonna get it done in 20 minutes, but let's give it a shot. So we're going to start mouse development at this point. And I just put these notes up. Just put these notes up right before class. So when you open the notes, be careful. The ink might still be wet on them. Haha, Dr. Slish. You're so funny. Okay, so quick review of mouse development. If you remember, it starts out with 1 cell, splits to 2, gets to the 8-cell stage. And then at the 8-cell stage, it undergoes this process called compaction, where the whole thing squeezes together. And that's going to be really important now for development, and we'll see why. What happens at this 8-cell stage is you end up with outside cells and inside cells, and they're going to be very different from each other. And then after it gets past this, okay, this is why it's important. After it gets past this stage, you end up at this stage, the blastula stage, and now you've got 2 very different cells here. You've got trophectoderm cells along the outside, and if you remember from chapter 3, they'll be involved in extraembryonic tissues and also implanting into the uterine wall. And then we've got these inner mast cells, some of which will become the embryo, some of which will also be extraembryonic. So let me pull up my notes to make sure I'm not forgetting something. Okay, so the position here is really important because if you are an outside cell, you're going to become trophectoderm. If you're an inside cell, you're going to become the embryo. Now you can take those early outside cells, push them inside, and suddenly they become embryo. So it's the position that matters more than anything else. So at this point, they're not specified, but because of their position, they become specified afterward. And here's how that happens. So at the 8-cell stage, early on, you've got 2 important transcription factors, CDX2 and OCT4. CDX2 is going to specify trophectoderm. OCT4 is going to be inner mass embryo cells. So whichever one is up is going to tell you what that cell is going to be. At this 8 cell stage, they're both expressed at a really low level. So neither of them is having any advantage here. As it gets to the 16 cell stage, now you've got a situation where you've got outside cells and inside cells. And in those outside cells, CDX2 is going to come up. And then the inside cells, CDX2 is going to go down and OCT4 is going to come up. So these two transcription factors inhibit each other. At first, they're both there, but then when it switches and you have outer cells and inner cells, the outer cells, CDX4 will come up a little bit, excuse me. And when it does come up, it'll inhibit OCT4. And in the inner mass cells, CDX2 doesn't come up, so OCT4 comes up and it inhibits CDX2. So once you get to the 16 cell stage, you end up with 2 different cells. And now they are, they're specified or fated to go on to what they're going to be. So again, these outside cells, CDX2 comes up, the inside cells, OCT4 comes up. Now at this stage, if you were to take these OCT4 expressing cells out, put them into another embryo, you'd find out they're still pretty much totipotent. They can do anything. They can produce trophectoderm and become a complete embryo. These ones on the outside, the CDX2 expressing cells, they're done. Okay, they're going to be trophectoderm. They are specified at this point and they can't change. So OCT4 is kind of a supports pluripotency. Whereas CDX2 is more kind of definitive. Once you're getting that, you're going to get there. Now, your next question, the question you're going to ask me next, I know, was why is it that the outside cells get CDX2 and the inside cells have OCT4? Well, this is really a really cool signal transduction pathway that we haven't seen before, and it's called HIPPO. Okay, so we're getting into these weird Drosophila names again. HIPPO, and what is the other one? Warts, HIPPO and warts. And there's some other weird names in there too that I'm going to skip. Okay, so let me see. Let's start here. Okay, so here's an outer cell, right? An outer cell's got a free apical membrane. So apical is outside, basolateral is inside. So inside is contacting cells here. The outside cells are contacting the inside cells, and they're also contacting the cells next to them. So on 3 sides, they've got contact with other cells. On the 4th side, they're wide open. So these outer cells then are going to have, well, all cells have got these adherens junctions. And we'll talk about these more in the next test. But adherens junctions are basically cadherins stuck out from one cell, cadherins stuck out from the other cell. They interact with each other and grab each other, and that holds cells to cells. I believe we may have talked about focal adhesions in this class, maybe not. Focal adhesions are similar, except they're grabbing extracellular matrix. These cadherins are cell-to-cell contacts, and they're like a whole bunch of these proteins focused into little spot welds that hold things together. So these adherens junctions then are holding these cells together. And I've drawn one at each contact point. They're like spot welds all along the way of these junctions, okay? So these adherens junctions are really important both for holding the cells together into a tissue, but also for signal transduction. This allows the cells to talk to each other, so cells know when they're connected to other cells and when they're not connected to other cells. So one part of this signal transduction thing is this KEM complex here, 3 different proteins. And they each have silly names, and I don't remember what they are, but KEM, 3 proteins. These are going to hang on to HIPPO. This blue guy here is HIPPO. And so when HIPPO is bound up like that, it can't do anything. Now we've got another, and HIPPO is a kinase. We've got another kinase here called WARTS, WTS. And because HIPPO's tied up, WARTS isn't doing anything. Downstream of that, you've got YAP. YAP is a transcription factor, and it interacts with TEAD. Okay, so these two come together, they form a transcription factor, and that increases CDX transcription. So because of that, CDX comes up and inhibits OCT4, and now you have only CDX2 being expressed in these cells, and they become trophectoderm. Now, if you're an inner cell, and I'll go over this again, if you're an inner cell, then that protein, this other protein that I didn't talk about here, AMAT, is in the outer cells, it's accumulated at this apical membrane that's not attached to anything. Now, if you're an inner cell, then that AMAT doesn't have that apical surface, and it binds to this KEM complex. When it binds to the KEM complex, it displaces Hippo, and Hippo phosphorylates warts, warts phosphorylates YAP, YAP gets ubiquitinated and destroyed, and then TEAD doesn't have its co-activator, so it doesn't do anything. So in this cell, you don't get any CDX being formed. You still have OCT4 being formed, and it inhibits CDX even further. So in these cells, they get only OCT4. Okay, is that complicated enough?
What about trophectoderm in this case?
So these are inner mass cells, and these are trophectoderm. So wherever you see CDX coming up, that's trophectoderm.
Okay.
And these cells, because they don't have CDX2, will be inner mass cells and therefore embryo. So let me just go over that again. So you've got your outer cells, which are expressed in CDX2, and your inner cells, which are expressed in OCT4. And CDX2 is definitive. It's making these trophectoderm. Okay, so if you're an inner mass cell, then you've activated the Hippo pathway. Hippo phosphorylates WTS, WTS phosphorylates YAP, YAP gets broken down by ubiquitination. Now that shuts this transcription pathway off that involves TEAD, so you don't get any CDX2. OCT4 increases, and that's an inner mass cell. If the cell is exposed to the outside, okay, so it's got one side of the cell is not bound to anything, okay, that makes this AMAT accumulate out there, and Hippo binds to the complex, and then Hippo's inactive. Since Hippo's inactive, WTS is inactive, YAP builds up in the cell, binds to TAD, and that causes transcription of CDX. And CDX inhibits OCT4, so these cells get only CDX. Let me just summarize that in the next slide, and then I'll break for questions. Hopefully you have some questions. I know this is complicated. Okay, inside cells are touching all around, and because they're touching all around, they activate Hippo. Hippo breaks down YAP, and so you don't get CDX being produced. You've got OCT4 there, and that inhibits CDX2. So this line like this is inhibiting, and a line with an arrow is activating. So over here, your outside cells, they're not touching on the apical side, and so Hippo is not active. Because Hippo is not active, YAP increases, and it binds to TD4, TEAD4, and then you get transcription of CDX2, and that inhibits OCT4. And here, because you've got CDX2, you're trophectoderm. Here you've got OCT4, your inner mass cells. See, this is why I wish we could talk about this in person, because at this point, typically, students pick me up on their shoulders and carry me out, cheering me on because they're so happy that they learned something interesting today. Not happening today. Let me block this for a second. I mean, go back out here. Oops, that's not what I wanted. Okay. All right, so we've got this. This is kind of complicated, and I went over it kind of fast. You got this little reactions thing down here on your lower right on your screen. Give me a thumbs up if that made sense. Give me a thumbs down if it didn't make sense. Yusuf's got it. Stefan's got his real thumb. Okay, we got some. Okay, looks like everyone's okay. Quick question from Kwame and Esha. CDX2 and OCT4 block each other, exactly. And that's why you get one or the other, okay? If Hippo is not active, CDX2 comes up and inhibits OCT4. If it's active, then you don't get CDX2 and OCT4 represses CDX2. Why does not touching make a MOT to accumulate? I don't know. I spent about 3 hours today researching this to figure out that pathway. No one's got it in one easy explanation. And yeah, that's what I came up with. So one paper talked about a MOT and a MOT being important for releasing Hippo. Other ones talked about Hippo in different ways. So, that's as good as I could get out of that one. Sorry. Okay, any other questions or comments? Abdou Sabor. Just from your picture, I can tell you're not sure. I can't see this picture. Just saying that. No question? Yusuf, you going away, Yusuf? He's had enough.
Nah, the quiz really was tough for me, but
yeah. Putting together those last couple slides was tough on me, but my brain is sore too. We didn't really talk about much.
Actually, you explained that pretty well. I actually understood that part.
Oh,
so
good. Thank you.
So I have a question. It's
Okay.
about a quiz, right? So question 3 was like, well, it's a topical cream you put on your face. Yes, it's going to affect the developing fetus. But like, if it's on your face, your skin, how is that diffusing all the way to the fetus?
Well, typically in medicine, they want to be hyper careful. Okay. Last thing you want is birth defects. And I can tell you a long story about that. Maybe I will. But the thing is, if you use it as a topical thing, you're not going to get a lot systemically. I mean, it is nonpolar. It goes through the skin. It'll get picked up by the capillaries and spread all over your body. But you're only putting a little bit here. So the dose that gets in your whole body is pretty low. But it's a pretty potent teratogen, chemical that causes defects. So they want to be really, really careful. There are versions of the drug that you can take orally as well. And those are definitely contraindicated in pregnancy. So let me tell you my pregnancy story. So when I was in grad school, there was this guy down the hall, Van Manen, and we always used to laugh at him. He was an old guy, kind of staggered down the hall, and you could smell alcohol as he went past. And no one could figure out what he did. He was a faculty member in the department, but he didn't teach any classes. He didn't have any research going on. He just came in drunk every day. So a couple of years into my grad school study, I asked someone about him. What's up with this guy? Well, he used to work with the Merrill Dow, and Merrill Dow developed this drug called thalidomide. I don't know if you've ever heard of it. But it was I think a histamine receptor antagonist or something, and it was supposed to be really good for first trimester nausea. I mean, most women when they get pregnant will be nauseous in their first trimester. Some will be extremely nauseous to the point of it becomes a health concern. So this was a drug that was supposed to help with that nausea. So they did their studies in hamsters and rats and mice, and everything came out fine. And they were working on getting it through the FDA, and they released it in Europe and Canada, although the FDA was still studying it. Turns out it caused this really horrible birth defect where people were born without arms. They'd have hands, but no arms. And their hands come right out of their shoulder like this. Same thing with their legs. So it was horrific. And so the company got sued, and he had some things written in his notebook that they were easy to misunderstand. And of course, if you got a lawyer, the lawyers made sure it was misunderstood. And so Merrill Dow got sued, lost a lot of money. And part of the deal with Van Manen, for some reason, was he came to our department and had tenure there and could stay the rest of his life. So, but his career was over. So if you want to read a really interesting story about birth defects and drugs, thalidomide is really, really a big one. So that's why, now FDA is really, really careful about anything that'll cause teratogenic effects because, bad.
So it's more like a precaution. It may not actually happen then.
Right.
Okay.
Yeah. What do they say? Abundance of caution. They always act with abundance of caution. First, do no harm, right? So,
Okay.
but I mean, that's a good point because, if like I've got asthma and if I'm having a really bad asthma attack, they'll give me systemic steroids, but they won't let you have them for a week and they clear everything up like that. Steroids are like magic. I swear to God. What is it? Prednisone, excuse me, clears it up like that. But you can't take steroids on a regular basis because it'll cause your bones to be weak. It reabsorbs calcium from your bones. So they give you the steroid inhaler. So the amount that's actually going systemic is small. Most of it's going topically right on the bronchi, which are the places you need them. So topical. I'm just talking because I have time to kill here. I got 4 minutes.
Sounds like pharmacology class.
Yeah, it's pharmacology. Isn't it wonderful? Pharmacology it's fun. It's good. It's like, if you do research in biochemistry, it's so esoteric and so far removed from actually changing anyone's life. But pharmacology is like one step behind actually a drug helping someone. So I think I like pharmacology for that reason. Okay, guys, I'm going to let you go. I don't know if you do anything Monday, but I'm going to be here at 1 o'clock Monday. If you're here, we'll talk more about mouse development. Talk to you later, guys.